Hi, welcome back to a new lecture from Computer Vision from Scratch. Today we'll be understanding about SqueezeNet and we'll implement it for our 5 flowers dataset. SqueezeNet is an amazing, very popular neural network architecture which convinced the deep learning researchers probably for the first time that even relatively small parameter neural networks with less megabytes in size can achieve similar accuracy as that of other popular neural networks, convolutional neural networks like AlexNet. So SqueezeNet is very popular, and when you implement the SqueezeNet architecture for our dataset, I really want to show you the results, and I want to show you the comparison of those results with all the architectures that we have tried so far, including ResNet, AlexNet, VGG, and Inception V1. So with that, welcome to today's lecture. The years 2012 to 2016 was sort of like a crazy period for deep learning research, because with the introduction of AlexNet in 2012, it revolutionized the way deep learning was utilized for computer vision, because it showed that deep neural networks can actually be trained effectively for making good predictions on images. And then models came later. There was VGG introduced in 2014-15, and then there was GoogleNet, which was also renamed as Inception V1. So the question is, if so many things were happening around that time in 2015, 2016, etc., and when these neural networks were performing really well in ImageNet challenge for classifying natural images, why did researchers introduce SqueezeNet, and what exactly is SqueezeNet? So we will discuss that in today's lecture. The main problem researchers were facing, especially in the deep learning community in 2016-2015 time, was the models like VGG, GoogleNet were kind of big meaning big in terms of number of parameters and megabytes in size. VGG had around 138 million parameters. GoogleNet had around 6.8 million parameters. So GoogleNet was significantly smaller in size compared to VGG, which was a big deal. And as we discussed in the previous lecture, GoogleNet won the first place in 2014 ImageNet challenge, and VGG placed second in the same challenge, right? So then the question was, if we are using these big models, it's very difficult to deploy them for small devices like mobile phones or Internet of Things, where you might be deploying small Raspberry Pi modules or low computing devices. So at the end of the day, if you want edge computing where the models are embedded within these small devices rather than somewhere in the cloud, you might need very efficient, smaller models. So, but the problem was small models were actually not very good at making classifications, right? So that is the whole reason why AlexNet was introduced in 2012. It showed that, okay, you can have deep neural network and you can train it efficiently and you can make good predictions. Then VGG took it one more level. It was an even bigger architecture, which showed that, okay, you just need simple 3x3 convolutions. You just stack them in series and you can get good results. And then GoogleNet showed that you don't just use 3x3 convolutions. You use 1x1 convolution, and then later 3x3, use 3x3, 5x5 convolutions, etc. in parallel. And then that Inception module you repeat in series, and then that can give good results. So all these things were happening. So why did people think of squeezing the size of the convolutional neural networks? It's precisely because they saw that neural networks were getting bigger and bigger and bigger. So if you really want to deploy it on devices, you have to have small models with very high accuracy. So the paper, which you can access from archive, it was actually titled exactly like this: SqueezeNet, AlexNet-level accuracy with 50x fewer parameters and less than 0.5 megabytes model size. It's amazing. Like, I have rarely come across paper titles which are as bold as this and as interesting as this. And the first author's name is Forrest and Iandola. I hope I'm pronouncing the name correct. This paper has now almost 11,000 to 12,000 citations, and it's a very, very good paper. So any paper with more than 1,000 citations itself is called as a amazing paper. Anything about 10,000 citations is a really top paper. So this paper is super famous, and so is the SqueezeNet architecture. So the goal was or what it achieved was AlexNet-level accuracy. So although AlexNet came 4 years before in 2012, it was very popular. It is still very popular. So beating AlexNet was really a benchmark. And the main thing was dramatically fewer number of parameters. So I'm going to show you a table, not right now, in the later part of today's lecture, where we compare the number of parameters, size, year in which it was introduced, who built it, etc. as a table where we compare AlexNet, VGG, Inception V1, which is also called as GoogleNet. And finally, we'll also have SqueezeNet as the fourth column. So we'll go through that. But basically, this hopefully the good, efficient, low parameter model will enable on-device deployment so that you can run neural networks on your phone rather than calling some API and accessing a model hosted somewhere on the cloud, right? So before we further go ahead in the lecture, I want to give you a small recap in case you don't remember what happened in the course so far, or in case you are watching this lecture for the first time in this course, right? So I'm going to give you a brief recap. If you don't want to go through the recap, feel free to skip it, but it will not take more than 5 minutes. So in this course, so far, we are exploring this 5 flowers dataset. There are 5 flower categories: daisy, dandelion, roses, sunflowers, tulips. And we are trying to perform 5 class classification using various neural network architectures. So there are only 1000 images per class. So total dataset size is not that high. It's only 5000 images. So it's not a very easy task to do, because usually you might need tens of thousands or 100,000 plus images for very efficient classifications. But this is good because this will really push our experiments to its limits. So what we did was we started with the simplest of models, like a linear model. So we had RGB images, and we first converted this into a flattened layer. So if we had n number of pixels across 3 channels total, then those n pixels will be converted into n by 1, sort of like a column vector. Then after this fully connected layer, after this flattened layer, we had a final 5 node output layer, and there was all the nodes in the previous layer was fully connected to all the nodes in the final layer. So there was no activation function, except in the last layer, we used softmax activation to convert the final output numbers into a probability distribution. That's it. But that softmax distribution was not affecting the way predictions were made. So in effect, this was a linear model without any activation. So when we implemented this model, we got around 40 to 45% training accuracy. Validation accuracy was 35-40%, not very high, but a random classification model, which is the worst model possible, it will have only 20% accuracy, right? Because there are 5 classes. So this is better than a random classifier. Loss was 10 to 20 in terms of magnitude. Then we decided, okay, just linear model is not enough. Let's introduce a hidden layer with 128 nodes. So after the flattened layer, we introduced a hidden layer with 128 nodes with ReLU activation. And this model actually did not perform that much better. You still had around 40-45% training accuracy, and validation accuracy was 35-40%, but surprisingly loss was 1 to 2. So an order of magnitude less loss, but similar accuracy. You might be wondering, how is this possible? This is possible because the model is still making similar number of accurate classifications. Because if, let's say, the true label is like this: class 0, class 1, true label is 1, 0, meaning this whatever is this data point belongs to class 0. And whether you are making this prediction or this prediction, accuracy will be the same, because 0.6 and 0.4 says that this prediction says that you are in class 0. Similarly, this also says that you are in class 0, but the loss will be lower in this case because here you are making a more confident prediction compared to this case. So this is in general what was happening in the a single hidden layer approach. Plus there was also a little bit of overfitting happening because the training accuracy was on an average 10% higher than the validation accuracy, which was not good. So then we thought, okay, how can we prevent overfitting? So then we introduced regularization, batch normalization, dropout, and early stopping. Early stopping was not needed anyways because we were only running for 10 epochs. So that was not significant, but we anyway implemented it, although it was not actually being utilized because we were not seeing accuracy drop because we are over training, right? That was not the case. The case was that the model was not good. Model was there were in few cases model was overfitting, but other than that, the issues were more related to dropout, batch normalization, and regularization. And in fact, we noticed that batch normalization worked the best in terms of increasing the training accuracy. So we saw that training accuracy could be taken up to 70%, and validation accuracy reached around 50-60%. Not good, not the best, but still okay. We did not get 90-95% accuracy, but we got like 50-60% accuracy. We were happy, but we were not completely satisfied. So this is when we truly realized that we have to do transfer learning, where you don't train the model from scratch, where rather you train the model on top of a pre-trained model. So you import a pre-trained model and then only train the last classification layer, so that rest of the model is kind of frozen. So here in transfer learning, we started with a ResNet model, and training accuracy actually reached 100%. Validation accuracy was 80%. Classic sign of a bit of overfitting, but still, because the validation accuracy and training accuracy tremendously improved compared to our previous case, we were happy, and we did not bother with hyperparameter tuning too much. We could get better training, or better validation accuracy, or lesser overfitting by a bit of hyperparameter tuning plus implementing some overfitting prevention tactics. But we did not bother that, because this proved the point that yes, transfer learning is what we have to do. Then we decided, okay, we are anyway going to do transfer learning, so let us start from the very first popular CNN models. So the most popular CNN model ever was AlexNet, introduced in 2012 by these three researchers. Alex, who after his name only AlexNet came. And then there is Professor Geoffrey Hinton, who was a Nobel Prize winner in 2024 for Nobel Prize in Physics. And Ilya Sutskever, who was also a co-founder of OpenAI. This paper is truly legendary with 170,000 plus citations. So this AlexNet model actually allowed us to get 95% training accuracy and 90% validation accuracy, the best model so far in the course. And the number of epochs for which we ran was just 10 epochs. Amazing. Then we moved on to VGG, introduced from Oxford University. And instead of 10 epochs, this time we ran 50 epochs, because we realized that for 10 epochs, the accuracy is not that high. But here we actually did not get much better performance compared to AlexNet, although VGG is supposed to be better than AlexNet. We got 85% validation accuracy and 75% training accuracy, which was due to underfitting rather than overfitting. It's a good problem to have, because this can be improved by running more number of epochs, like 20 epochs, 200 epochs or something like that. But we decided not to do that, because already implementing this was taking 4.5 hours. And it makes sense, because VGG is a very big model, so training will take time. Although we are freezing most of the layers, the final layer is still bigger. The final few layers are still big. So this training was taking time. But we were kind of happy with the validation and training accuracy that we were getting, although surprisingly, VGG did not come as close to AlexNet. Then in the previous lecture, we did implement GoogleNet, also called as Inception V1. And here, actually, we got decent results without overfitting or underfitting. We ran for 50 epochs. We got 86% training accuracy, 87% validation accuracy. Pretty good. We are very happy with this. And maybe with a bit more hyperparameter tuning, these numbers can be pushed to 95%, 95 or beyond. But we did not do that, because our whole point is to walk all of us through different CNN models with transfer learning approach, because in all these cases, we are using pre-trained models. We are not training from scratch. And it proves our point that yes, all these models, because we are not training from scratch, is able to achieve decent validation or training accuracies. Now, after this only comes our current lecture, where we are going to look at why did SqueezeNet come into existence, as we slightly discussed before, and what exactly was its architecture and what did it accomplish. So this is what we are going to look at in today's lecture. So before starting to look at SqueezeNet, let me remind you once again, and this is for all of us, that there is a reason why we started this course, right? We really want to master computer vision. So please remember why you started this course. There are hundreds of thousands of people who start courses, but very rarely people finish all the way till the end. So please remind yourself of this fact that you have started with great seriousness, and let us continue for the same reason why we started. So let's take a pledge that we will finish what we have started, and you will be with me throughout till the very last lecture of this course. And if you are trying to study computer vision with a friend, try to keep each other's accountable for finishing lectures and doing the exercises. Otherwise, if you are alone, if you are studying alone, you can make yourself publicly accountable by just making a small comment saying lecture 10 or lecture 11 finished, just something like that. And then hopefully that will fuel your motivation to continue lectures after each lecture is finished. So I really want you to internally or externally take this pledge so that you are kind of motivated to finish this. Now, coming back to AlexNet. So AlexNet had some kinds of similarity with, coming back to SqueezeNet. SqueezeNet had some kinds of similarity with Inception V1, also called as GoogleNet. So in the previous lecture, we discussed about this Inception V1 module, where if you had a previous layer, this layer was parallelly processed through these four filters, one by one convolution. Then let me open my pen. So this one by one convolution, this one by one convolution, another one by one convolution, and here there was max pooling. And then these three were again passed through 5 by 5, 3 by 3, 1 by 1 filters. And finally, you concatenate all of this. So if you look at the dimension 64 plus 128 plus 32 plus 32, that will be 128 plus 128 equal to 256. So in the concatenated version, the final channel dimensions will match up. So, and this one by one convolution was a very innovative thing to do, because using one by one convolution and with a smaller channel size, so here it is 96 instead of 192, you can reduce the number of parameters. So Inception V1, for this reason, it was able to capture local features, because one by one is a small convolution, right? It's just looking at 1 pixel, whereas 5 by 5 convolution is looking at 25 pixels. The filter is seeing 25 pixels at the same time, right? So it can capture kind of more global features, whereas one by one convolution can look at local features, or smaller convolutions can look at local features. And this enabled Inception V1 module to learn more patterns in the image dataset without having to have so much depth, similar like VGG. So this one single Inception module was repeated in series again and again and again and again to build the entire neural network architecture. Similar to Inception V1 module, in SqueezeNet, you have something called as Fire module. So this Fire module is something where you first squeeze using a one by one convolution. And here you can see that the number of channels have been squeezed. And then this squeezed layer is expanded by parallelly processing through another one by one convolution and 3 by 3 convolution. And then they are stacked on top of each other. So this and this are stacked on top of each other to expand. So squeezing and expansion. So this is the basic module or basic unit of the SqueezeNet architecture, which was named as Fire module. And then in the entire SqueezeNet architecture, which I will show you in the later part of this lecture, you will see how this Fire module is repeating again and again and again in series. And overall dimension, overall number of parameters of the SqueezeNet architecture is also significantly lower compared to VGG architecture, or even compared to Inception V1 module, right? So why does this work? Because as we discussed in the last lecture, which I will show you again with a numerical example, one by one convolution will help you drastically reduce the number of parameters. And then 3 by 3 convolution is only applied to fewer number of channels. So number of channels you can imagine to be this depth, you can imagine to be the number of channels. So here you have 1, 2, 3, 4, 5, 6 channels. Here you have 2 channels. Then this 3 by 3 convolution is applied such that the final output has 3 channels. Then this 1 by 1 is also done such that this output has 3 channels. And total, when you concatenate 3 plus 3, 6 channels. So 3 by 3 is only applied to fewer channels. And then output is rich in multi-scale features. What do we mean by that? Multi-scale. Multi-scale meaning local, global features, because 1 by 1 is more local. 3 by 3 captures features across a broader region because that filter is bigger. So you have multi-scale features and you are concatenating them. So that way, this whole stack will have information about different types of features in an image, different scale features in an image. So this is the reason why the SqueezeNet is proposed to be working. But I'm pretty sure some of these conclusions are also in retrospect, because I'm pretty sure SqueezeNet, before coming up with a successful SqueezeNet architecture, I'm sure researchers would have tried similar versions which did not work, and the same reasoning that we are applying probably did not work in that case. So although the reasoning is good for us to understand why something works, in my experience, it almost always comes in retrospect. So, but in any case, it's good to think of why this architecture is working, because only then we will be able to make newer and newer architectures, right? So this is an example of SqueezeNet efficiency in terms of number of parameters. So we had discussed in the VGG lecture that it uses 3x3 convolution throughout, right? So it made the architecture very simple, just 3x3 convolution filters applied over many deep layers. So that was a simplicity in terms of convolution filters, but it showed that you don't need fancy convolution filters, you just need proper depth. That's what VGG tried to show. Inception V1 showed that, okay, no need to blindly go with depth. Go with different types of filters such that you can capture both global and local features. So this multi-scale features will allow neural network to learn patterns more efficiently from images. Now in SqueezeNet, we are having, yes, 1x1 filter. So let's think that if we had a 3x3 convolution over 256 input channels, that means you will have 3 multiplied by 3 multiplied by 256, roughly 2304 weights, these many parameters. But let's say we use a SqueezeNet layers to reduce, instead of 256 channels, we reduce to 16 channels. Then how would it look like? Then 1x1 convolution applied over 256 channels means you will have 256 weights, but then you are reducing it to 16 channels. So then the 3x3 convolution is applied over 16 channels. So 3 multiplied by 3 multiplied by 16 equal to 9 multiplied by 16, 144 weights. So if you add up 256 plus 144, you have only 400 weights, which is 80% smaller compared to 2300 weights. So if you use this 1x1 convolution before and converting it to 16 channels before sending to 3x3 filters, you can significantly reduce the number of weights or number of parameters. So similar idea, Inception in 2014, 2015 did exactly same thing, unlike VGG, but same thing is applied in SqueezeNet, but this was in 2016. And in SqueezeNet, every single module had significantly lesser number of parameters. So this is what Fire module enables you to do, less number of parameters, but multi-scale features. Now in SqueezeNet, what did they accomplish? They accomplished, as the paper claims, AlexNet-level accuracy. So the top 5 accuracy in ImageNet competition was 80%, 80 or 83%, and there were only 1.2 million parameters. I'll show you like the proper comparison between these 4 architectures. AlexNet had around 60 million, VGG 138 million, Inception V1 had 6.8 million. And the model size in megabytes was 4.8 MB, which makes it very much suitable for mobile phone based applications, basically lightweight applications. And this also inspired like future models like MobileNet, which was very famous, ShuffleNet, which is also kind of famous. So let's look at this table, right? 2012, everything started with AlexNet. So each column corresponds to one CNN architecture: AlexNet, VGG 16, Inception V1, which was GoogleNet, and SqueezeNet. AlexNet was in 2012, VGG was in 2014, 2015 that time, Inception V1 same time, 2014, because they were both competitors in the ImageNet 2014 competition. VGG placed second, Inception V1 placed first. Then 2016 came SqueezeNet. SqueezeNet actually did not win any ImageNet challenge, but still, if you look at this accuracy, it's not 83 accuracy, it's 80.3% accuracy. So top 5 accuracy was similar for AlexNet and SqueezeNet. But look at the number of parameters. AlexNet 60 million, VGG 138 million, Inception V1 much smaller, 6.8 million. This is truly amazing because the top 5 accuracy was very high, number of parameters were significantly low, but SqueezeNet was even smaller, 1.2 million. And when you look at the depth, right, AlexNet had 8 layers. The depth was 8 layers. VGG had 16 convolution layers, as the name suggests, VGG 16. Inception V1 had 22 layers, but it was not like a mindless addition of convolution filters. There were individual inception modules. And in SqueezeNet, there are 8 fire modules. So fire module architecture you saw above. And the core innovation was in AlexNet, they showed the ability for ReLU, dropout, pooling, and parallel processing using GPUs to be effective while training deep neural networks. So this is the first time CNNs were proved undoubtedly to be superior compared to hand-engineered features for image processing. So AlexNet is still the OG. And then VGG showed that just 3x3 convolution filters are enough. You don't need fancy filters. Inception V1 introduced Inception module, which was parallel processing for multi-scale features. And in SqueezeNet, you had 1x1 squeezing followed by expansion using 1x1 and 3x3 convolution called fire modules. And AlexNet proved CNNs being working. VGG 16 allowed the models to go deeper. Inception was more efficient in terms of parameter size, but multi-scale features, local and global features. And SqueezeNet shrank the model size even further. And the people who introduced was AlexNet came from University of Toronto, VGG from Oxford VGG group. I think it's called Visual Geometry Group or something. Inception V1 was from Google, as the name suggests. And then SqueezeNet came from UC Berkeley plus Deep Scale collaboration. So this is in a nutshell how things progressed during the years 2012 to 2016. ResNet came later, so we'll be discussing about ResNet also in the subsequent part of the course. And of course, we can have a discussion about MobileNet as well. Not in this lecture, in the later lecture. But yes, SqueezeNet did not win ImageNet challenge, but still it accomplished something that many other models never accomplished. It was a very small, lightweight model, which could do amazing things. This is the entire architecture of SqueezeNet. So you have, look at this fire modules. You have 1, fire 2, fire 3, 3, 4, 5, 6, 7, 8, 8 fire modules actually. So you have convolution, max pooling, then fire modules. Here is max pooling. Then after 4 more fire modules, there is max pooling, then fire, convolution, softmax. And if you ask me, like, how did people come up with this architecture? How did they know that this architecture works? I'm sure there was a lot of trial and error involved. Of course, people who worked on this was genius and they had a lot of intuition to build this in the first place. But I'm sure there was also like a lot of trial and error involved, just like how people built GPT. So that's how human knowledge progresses, right? You don't sometimes come up with innovation. You stand on the shoulders of giants. So people do some work and then the people who follow build on top of it. So SqueezeNet is also, I'm pretty sure it's like a fairly good example of building on top of things and coming up with a new innovation which people could not build before that time. So now with that, we can implement the SqueezeNet. I have already implemented and I will show you the results. And as the size suggests, SqueezeNet implementation was much faster compared to VGG, and it was also faster compared to Inception. So here in the code block, I'm just showing you the relevant parts. I'll show you the Google Colab code and I'll share the code also with you so that you can run it. So the relevant parts are this. As you know, we are logging all the experimental results into weights and biases. So the project name I have just changed to SqueezeNet Flowers. Then architecture, this is just just to show I'm not using this parameter anywhere in the code, just to quickly allow me to understand that, okay, I am following SqueezeNet in this code without looking at the rest of the code. I just need to look at the weights and biases configuration, this part. And epochs, I'm running 50 instead of 10. Initial few models, we were running 10 epochs. Now I have increased to 50. Batch size 16, learning rate 0.001, and input size is default itself was 224 by 224 by 3. So I'll keep it as such. And here again, pre-trained true. That is also not used anywhere, but I'm just mentioning it here to show that, show to whoever is reading the code in the beginning itself that this is a part of transfer learning process. And then the other part where we have differences in the code compared to the previous code files was we are importing SqueezeNet 1 weights rather than ImageNet weights. Previously, we were importing GoogleNet weights. And then from models library, we are importing models object, we are importing SqueezeNet 1. And in SqueezeNet, we have weights as the parameter where we are passing the default weights from the imported SqueezeNet 1 weights. And then we say the final layer should be a 5 class classification layer. So the number of output channels in the final layer is 5. Then we say, okay, we freeze all the parameters except the parameters in the last layer. So we freeze all the parameters first and then unfreeze all the parameters in the last layer. So before showing you the full code, I want to show you the results, and the results are the happiest. In fact, SqueezeNet has outperformed all the other models that we have implemented in this course so far. Of course, I know that it's a bit apple to orange comparison because we are running 50 epochs. Previously, we were generally running for 10 epochs. Even the AlexNet we had run for 10 epochs. So I know that it's an apple to orange comparison, but I am glad that we are going in the better direction. So we have 94% as the training accuracy after 50 epochs, and we have 92% as the validation accuracy after 50 epochs. It's really, really amazing. I'm sure with a bit of hyperparameter tuning, like playing with learning rate, implementing dropout, or maybe playing a bit more with not in the frozen layers, but in the final layer of classification, implementing some regularization techniques might work. I don't know. We have to try, but I'm already happy with the general direction that we are taking in this course. We are at close to 90-95% accuracy. Our ultimate aim is to have really good models with 99% accuracy, and I'm sure we will get there. We will play with different models and we will see what all things to make better. But I'm very glad with this result, and the conclusion is obviously this is the best model so far that we have tried. To execute the code, which I'm going to show you, it took around, I think 45 or something minutes. So this is the code file. I'll share the code file with you. So everything is fixed as before. We have connection to the Google Drive because all the data image files are in Google Drive. Then we have weights and biases initiation, and you have to connect with the weights and biases, and in that you will need to get the API key. So weights and biases I'm using to log the experimental results, as you know, and you can get the API key by going here in quick start WNB models. Here you can get the API key. So use that API key to log your results. So when you run this block of code, it will ask you to paste the API key. Rest of the code remains the same. You have standard image pre-processing, resizing, which does not do anything here. You are resizing it to the same size. Random horizontal flipping, then normalization using these parameters. That is done for both training and validation images. And then here is one part where your code might differ. So I have stored this 5 flowers dataset in some Google Drive file, right? I'll share the file link with you. You can copy it, and you can duplicate it and put it somewhere in your Google Drive. So this path might differ based on where exactly in your Google Drive are you pasting it, right? So this train directory and validation directory. Other than that, everything in the code will remain the same. And this name also, project name, you can name according to whatever you want in your weights and biases. Then we load the pre-trained model. So we import SqueezeNet weights. Model is models.squeezenet. And then rest of the things remain the same. And then we have cross entropy loss, Adam optimizer, and then we train the model in this function. And we print the epochs accuracy once in every 10 batch sizes. And then after the entire batch is finished for each epoch, we print the accuracy. Like that, we run for 50 epochs, and you saw the accuracy, 94-95% in training, 90-91% in validation. Really, really good accuracy. So feel free to run this code. I'm sure you will enjoy this whole process of running. I am running with T4 GPU, which is available for free. You don't have to pay. So you can also try the same. And yeah, basically that's pretty much it. I think from where we started with the linear model with 40-45% accuracy, we are at a very good place, right? And I knew that transfer learning would have worked really well, but I was skeptical. Okay, what if this data set is not really suited for the kind of models that we are using? I was not sure how much hyperparameter tuning we'll have to do, but turns out we don't have to do it so much because the pre-trained weights are already so good, and the kind of images we are using are natural images, like flowers. They are naturally occurring images, images of naturally occurring things, right? So the pre-trained model weights are already really good because they are pre-trained probably on ImageNet, and they are all images of things occurring naturally. So it's very good. I think we are at a good place. In the subsequent lectures, we will look at ResNet. We will also have a brief look at ImageNet before proceeding further ahead in the course. But before winding up the lecture, I really want to take one more minute to congratulate you. We are actually here. You have finished 11 plus lecture 0. So 12 lectures. And more than 33% of the course is hopefully finished now. I don't know the exact number of lectures because some concepts are taking more number of lectures to finish, but I'm hoping that I can wind up the course in around 30-35 lectures. We'll see. In any case, you can consider yourself to be done with 1/3 of the course, and I'm sure you should feel very good about yourself. I'm very happy that you are following throughout with me throughout this course, and I look forward to seeing you in the subsequent lectures. Please take care. Hope you are enjoying the series, and we'll meet again in the next lecture. Thank you so much.